hardest thing about limits is just learning the new notation. I think once you get the notation down and understand what it's asking for, you guys are good at algebra, and so this tends to be really pretty darn easy, okay? But it's not going to feel easy at first when the notation looks new. So let's talk about the notation and what we're actually looking for when we ask for a limit, okay? So it says the limit as x approaches a is a two-sided limit operator in the limit as f of x as x approaches a, because we must consider the behavior of the function as x approaches a from both the left and the right side. The limit of the function f of x as x approaches a. Okay, so let's, let me get some, it's hard in just words, so let's talk for a second about a picture. If I had a function, let's start with an easy one with our linear parent function. If I said f of x equals x, this is just the linear parent function, y equals x. Okay, we have it graphed there, okay? So when we ask for the limit of as x approaches a number, and this is what the saying is, x approaches a. So let me say that this is 2, and so of course we know that that would cross at positive 2. Okay, so when we ask for the limit as x approaches 2 of the function x, okay, the limit as x approaches 2 of the function x. Okay, so here I picked an actual function to list for here, and so that was the function equaling x. Okay, so here's my function. It's just a simple one. The limit of that function as x approaches 2. And what this first thing is saying that that's a two-sided question. So the limit is what it's approaching, what value it's getting closer and closer to. And so we have to look at what it's approaching from the left and what it's approaching from the right. And if those two sides are approaching the same number, then that function has a limit at that value that we're checking it for. Okay, so this says the limit as x approaches a from the negative. Now, this has a negative in the exponent's position. So let me write this a little bit bigger for you. The limit as x approaches a, and the negative sign indicates that we're coming from, if you think about your positive numbers on the right and your negative numbers on the left, that means we're approaching from the negative side or from the left side. So that means we're approaching from the left side. Okay, so the limit as x approaches a from the left side is a one-sided left-hand limit operator. We read that as the limit of f of x as x approaches a from the left. Okay, so the little negative sign in the exponent's position just tells us we're approaching from the left. The limit as x approaches a from the right. Okay, so I'm going to write that again a little bit bigger because I think it's really small there, as x approaches a from the positive side. So from the positive side is the right side, whereas from the negative side is the left side. Okay, so we're approaching from the positive side, we're approaching from the right side. Okay, that's a one-sided limit. It's just asking what does it approach from the right side. If we say from the left, we're asking just what does it approach from the left side. But if we ask just what does it approach as it approaches a, then we're asking it's got to be an agreement what it's approaching from the left side and what it's approaching from the right side has to be the same answer. And in this simple example that I gave you, it would be the same answer. As we approach from the left, it's getting closer and closer to that value. As we approach from the right, it's getting closer and closer to the same value. And it is, in fact, that value. But we're going to look at a lot of different graphs and equations today where it's not always so simple as equal to the linear parent function. Okay, so let's go look at one more talking slide, and then we'll get looking at actual problems, and I think you'll find it's much easier. So just don't stress quite yet. I know it's a lot of new notation, feels a little unfamiliar. Okay. And let me advance the slide. There we go. Okay. The existence of a two-sided limit at a point. The limit of a function as x approaches a equals capital L, which stands for the limit, whatever that limit equals, and that just stands for the limit. And this is our notation way back from geometry, when our logic days. That's our two-directional arrow. That's our if and only if. IFF stands for if and only if. So the limit equals L, if and only if the limit of the function as x approaches a from the left is L, And the limit is f of x as x approaches a from the right is also L, meaning it's got to approach the same number L from both the left and from the right to equal the limit of the whole function. Okay, it's got to be both. And that just defines A such that the limit is an element of the real numbers. Okay, so we're talking about real numbers, not imaginary numbers here. Okay, a two-sided limit exists if and only if the corresponding left-hand and right-hand limits exist and are equal. If either one-sided limit does not exist, D and E stands for does not exist, or if the two one-sided limits are unequal, then the two-sided limit does not exist. And this is going to be easiest to see when we do some graphical ones here in just a second, okay? So if the limit of x plus 3 as x approaches 3 from the left is 6, and the limit of x plus 3 as x approaches 3 from the right is 6, that implies the limit of x plus 3 as x approaches 3 overall is 6. Okay, and so that's how we would read that. That's how we would say that. So let's try some with pictures, because like I said, I think once we actually get going, you'll feel a little more comfortable when we're seeing like what we're actually talking about. It's good to be able to read through a formal definition. I would recommend at the end of class, you come back to those definitions and try reading them through and see if they make sense once you have a better idea of what it is they're trying to say. All right, now I know this writing is super small here, so I'm gonna write bigger what we're doing on each one. Okay, but here's our graph of our function, and they want us to find the limit, each of these different limits for this function. So this is our function f of x. It's a piecewise function. It's got different pieces to it, but it's all our function. Okay, so this is the limit as x approaches, I don't want to write it that big. Just get a regular pen and write it. As x approaches 3 from the right, okay? This is the limit as x approaches 3 from the left, and then this is the overall limit as x approaches 3. Okay, so let's look at that first one. Okay, so if I want to see graphically the limit as x approaches 3 from the right, I'm going to start on the positive side of my graph, the right side of the graph. This is my left side. So coming from the right side of my graph, the positive side, towards an x value of 3. Okay, so here's my x value of 3. So I'm going to put my finger on my graph and start approaching 3. And what value are we approaching? We're approaching a y value of 3. Okay, a y value of 3. Questions on that so far? As we come from the right side, it's approaching 3.
Since the other one on the x, it's the x root of 3, the black dot, the black point. Since it's coming from the left side, is that negative, I'm guessing?
No, I'm not sure. Let's go through. Let me actually just go through this first example and then see if that answers your question. If not, then you can ask again, okay? So on the next one, number 2, it says the limit of the function as x approaches 3 from the left side this time. Oh, is that what you meant? Like you said negative. It's from the negative side of your graph. That's just, they use that negative notation. All it means is from the left. It doesn't mean negative. It means from the left, okay? But we can intuitively remember that because the negative side is on the left side. So that's why I said coming from the right or coming from the left. And the positive and negative make good notation symbols to mean from the right and left, because we're used to thinking of positive numbers on the right and negative numbers on the left on our number line. But literally, this reads the limit of the function as x approaches 3 from the right. This next one that we're about to do is read the limit of the function as x approaches 3 from the left. So we don't read that as negative. We read it as from the left, but it is coming from the left side, which we usually associate with negative, okay? Just a little technicality. All right, so let's try the next one. If I put my finger on the graph and I'm approaching 3 from the left side, what number are we approaching? We're approaching the number 2. Okay. This is number 2 from the left side, approaching 3 from the left. So here's my value 3, and I'm approaching it from the left side. As I get closer and closer to it from the left side, it's approaching this value, which is 2. I am. I'm coming from the left side. I'm sliding on in this direction from the left side. As x approaches 3 from the left side, the value approaches 2. Remember, our f of x notation we're used to thinking of as y equals notation. So it's asking, as x gets closer to 3 from the left side, what is your y value? And my y value is 2. I know, it'll just take a little practice, and then you guys will be like, got it. Okay, but it does take a little practice at first. Okay, so we've looked from the left and the right, and now the question is, what is the limit of the function at x equals 3? Well, those two slides we've read so far said that it has to be approaching the same value from the right and from the left to have a limit. So this function, because those are not equal from the left and right, does not exist. The limit of this function at 3 does not exist. Okay, so we're going to try that again with another couple numbers. So this next one is asking as x approaches 1 from the right, as x approaches 1 from the left, and as x approaches 1 overall. Okay, so for the overall limit of that number to exist, it's got to be the same from the left and from the right. Okay, so let's try that first one. As x approaches 1 from the right, so I see my x value of 1. This is the number we're looking at. As we come in from the right side, what are we approaching? A y value of 0. Okay. As we come from the left side, approaching an x value of 1, what are we approaching? Still a y value of 0. So what is the overall limit of that function at 1? It's 0. So the left side and the right side have to be equal, and if they are equal, then that is the limit at that value. Okay. All right, let's try another one. Okay, so let's try this next one. Is the limit as x approaches 2 from the right, as x approaches 2 from the left, and as x approaches 2 overall. Okay, so I'm going to let you try to help me with this one. So Alex, what's the limit as x approaches 2 from the right? So find an x value of positive 2. Okay, as we approach from the right, what are we approaching? A y value of 1. As we approach from the left, still 1. So that means the limit of the function at x equals 2 is yes. Questions for me so far on that? Emily?
Getting the right side, but can you just go like point how you're doing the left side?
Okay, so the left side just means as I come from the left. So I know I'm looking at this x value, so I put my finger anywhere to the left of it and I start approaching that x value. So as I approach that x value of 2 on my graph, my y values are approaching 1.
How do you finger to start though?
Anywhere to the left of it. Because it doesn't matter how far over you pick, it's as we approach 2, so we don't care until we're getting super close to 2.
Okay, that makes sense.
So it's just as we approach 2. As we get really close to 2, where are we?
Okay, thank you.
Okay. All right, so then the next one, now that we've done a couple where we've done 3 separately, we're going to try looking at a couple individually. And I have to even check my own where I wrote down which ones those are because those are kind of hard to see, super small. Okay, so this next one is asking for the limit as x approaches -1. Then we've got one for x approaches -2. We've got one for x approaches -3 from the right. X approaches -3 from the left. And x approaches -3 overall. Okay, so that's what those next few are coming up. So let's take a look at this one and see. Now we're asking overall, what's the limit of the function as x approaches -1? So help me with that. Sarah, what would the limit be as x approaches -1 overall? So to be the limit overall, it has to be the same from the right and the left. If it's a continuous function, it's pretty easy to see the limit because you just look at x equals -1 and what value we're approaching, both from the right and from the left, you're approaching that same value because it's continuous. Can you see that? Okay, so this time it would be 0. So the limit of f of x as x approaches -1 is 0, okay? What about the limit of the function as x approaches -2? Alex, you want to try, or I already did Alex for one. Zach, you want to help me with that one? As we approach -2, what's the limit? Yes, okay? So whether you're approaching from the right or the left, you're headed to a y value of -1. You're headed to a y value of -1. Questions from anybody on that one? Very nicely done, sir. Okay, so why do they want us to go right, left, and total on this next one? Let's see. Surely there's something different about it. Let's take a look and see. Okay, can you help me with the limit of the function as x approaches -3 from the right side? From the right side, what is it approaching, Nicholas? As we approach -3 from the right side, Nicholas, where are we headed? Where are we headed? 0, that's right. Okay, what about the left side? Where are we headed there, Nicholas? As we approach from the left side? 2, good job. Okay, and so if we are different answers from the right and from the left, if we're not approaching the same value, then what's the limit of the function overall at x equals -3? Well, if they don't match from the two sides, then the limit does not exist. The limit does not exist. That's right. Excellent. Good job, sir. And good job, Shay, too, for getting that. Okay, now I think there's a good example on this graph. I think, is it on this one? Maybe on the next graph. Let me see. I wrote in an extra problem for us. Oh, yeah. No, I think on this graph, let's talk about an extra problem that they didn't write in that I think is helpful to look at. Okay. What's the limit as x approaches 0? What's the limit of this function as x approaches 0? Okay. If we take a look at that, if we're coming from the right, I can see it approaches 2. If we're coming from the left, I can see it approaches 2. And the limit actually is 2, even though the function is discontinuous at x equals 0. Okay. If the limit from the left and the right are the same, then the limit exists, and that's the limit. So the limit of the function as x approaches 0 is 2, even though f of 2 is undefined. Even though f of 2 is the function evaluated at 2 is undefined, that doesn't matter. If we're not talking about what the value actually is, we're talking about the limit, which is what it's approaching. And it's approaching 2 as you get closer and closer to it from either side, it's approaching 2. And so it's not what the function actually exists at that number, it's what it's approaching. Okay? Questions about that? All right. So let's try. So how do you guys feel? I've got a whole nother slide of this if we need to do more of these graphically, or we can move on to doing them from equations. How do you guys feel? Do you guys want more practice with this right now, or are you ready to move on? Anybody? Like, I feel like it's pretty straightforward, but would we like more practice? Yes, no? Okay, so a couple nods, yes, yes. Okay, yes. If you want more practice, we can do more practice. So let's try this again. So I'm going to let you guys help me with this. Let me write it big on the screen so you know what we're actually looking for. So this first one is the limit as x approaches 2 from the right. And they called this function g of x as x approaches 2 from the left and as x approaches 2 overall. Okay. Then we've got the limit as x approaches 1 from the right, as x approaches 1 from the left. And it is supposed to be written small underneath, teeny tiny like a subscript. So that's the correct sizing on the notation, but when we've got it so small on the screen, that's why I'm writing it bigger. But the correct way it should look to scale like that, small like that, okay? So just don't want it. And then we want the limit as x approaches 1 overall. And then let's do the limit as x approaches -1 overall. The limit as x approaches -2 overall. And then just the function evaluated at -1 and the function evaluated at +1. Okay, so let's go look at a few of those and let me have you guys help me. Okay. Omar, can you help me with this first one? What's the limit of g of x as x approaches 2 from the right? So we need to find our x value of 2. Here it is. And we want to start coming from the right side. So what is that limit? And Gary said he found it. It's 2. What about if we come from the left side, Omar?
2.
Still 2. Which means the limit of g of x as x approaches 2 is?
2.
Beautiful. Okay, let's try another one. Sanjita, can you help me with this next one? Let me erase some of my stuff here. What's the limit of g of x as x approaches 1 from the right? Sanjita, so we've got to find an x value of 1. As we approach that value from the right, what is the limit of g of x as x approaches 1 from the right, Sanjita?
-1.
So be careful. So the right side is the positive side. The left side is the negative side. As we come from the left side, it approaches -1, but that's from the left side. This would be -1. I asked from the right side, which is kind of like the positive side. So look at that again. As we come from the right side, what is it approaching?
+1.
Yes. Okay. So it's +1 from the right. It's -1 from the left. So what does that mean about the limit of the function as x approaches 1? If it's not the same from both sides, then we say what? D and E for does not exist. It's got to be approaching the same value from the left and right for it to have a limit at that point. Okay.
So the open circle means that it could be a D and E.
It's not the open circle that means it. What means it does not exist is that it's not approaching the same value from the right as it is from the left. The limit from the right and left have to be the same for the limit for that x value to exist.
Oh, okay, thank you.
Okay, all right. And so let's try another one. Shay, can you help me with this next one? It's the limit of g of x as x approaches -1. So it's asking for the overall limit. So as x approaches negative.
Yeah, so it would be as x approaches -1, wouldn't it be -2 then?
Exactly, it would be. Because as we approach -1 from the right and left, we're still headed up to that same place. We're headed to -2. Now, I want to point out that if it's a continuous function, if it's connected and continuous, at least on the area that we're looking at, then where the function actually exists there is also the limit. So here, right below that, it asks for f of -1. F of -1 is -2. So the function evaluated at -1 and the limit as it approaches -1, it are the same if it's continuous on that piece of the graph. If it's continuous on that piece of the graph. We saw it on the last slide. Let me see if I can go back to that real quickly, where it was not continuous at that point. So there was a hole in the graph. So that's where we said the limit at 0 was 2, even though f of 0 was not 2, even though f of 0 was discontinuous. Okay, so let's go back and finish up this slide. Okay. So then what about the limit of g of x as x approaches -2? Taryn, can you help me with that one? What's the limit of g of x as x approaches -2?
G of x approaches negative. Okay, yes. Hang on.
Now, they didn't break it down for us. They just asked overall, but you still have to consider, is it the same as we're coming from the right and left? And as we approach -2, is it the same as we're coming from the right and the left?
Isn't it just a negative number? So doesn't that mean we're approaching from both sides? Yeah, sorry. I mean, because it's not a.
It doesn't say from the right or left, so it is asking overall. So does the limit, so what's the limit of g of x as x approaches -2? So the only way that it has an overall limit is if it's approaching the same value from the right and left. So at -2, is it approaching the same value from the right and left? If you're not sure, break it down. Okay, if you're not sure, break it down. Go ahead and find the limit.
Do they both get reached -1?
They don't both do the same thing. So let's look at it. The limit as x approaches -2 from the right of g of x. And the limit as x approaches -2 from the left of g of x. Okay, so from the right, what is it, Taryn? If we come in, if we're approaching -2 from the right, what value are we approaching?
-2.
We're approaching a y value of 0. Remember, your g of x notation is like your y equals notation. So as x approaches -2, the y approaches 0. Can you see that? Yes, no, maybe so? So Taryn, see the g of x notation is like y equals notation, so we're looking for the y value there. So as x gets closer to -2 from the right, what's my y value? So as we come from the right, we're getting closer and closer to a y value of 0. What about from the left side, Taryn? Okay. As we approach -2 from the left side, what's our y value approaching?
1.
It's +1. We're approaching a y value of +1. And because it's not the same from the left and from the right, what do we say? We say the limit of g of x as x approaches -2 does not exist. It's got to be the same as it approaches from the left or right to exist. So that does not exist. Like I said, if you have a little trouble, if you're not sure, then go ahead and just see what it is from the right and from the left. And if they don't match, then it doesn't exist. Okay? Here they did ask what is the function's actual value? The function's actual value at 1 is this closed circle up here at 1. So the function at 1 is 1, but the limit as we approach 1, as we approach -2 does not exist. Questions for me on that? Where I found what the function actually equals? Yeah. Sure, let me erase a little bit so we can see the original. So when we have f of x notation and they've actually plugged a number in for x, this just means the function evaluated at 1. So I go to an, sorry, and I think, oh, I thought they were asking about -2 there. So sorry, just a second. I answered the wrong question. I thought it was like this one matched with this one. So I thought this one matched with this one. So I didn't read carefully enough. So here they were asking a different question. So here they were asking the function evaluated at 1. So let me go look and see what it is. So at an x value of 1, we're actually here down at -1. So this would be -1. So we just go see where the closed circle hole actually is, if there's a closed point plotted anywhere for it. Okay, it's possible that the function is undefined at that value as well.
Okay, so you're not talking about or not on the open circle?
No, the open circle is non-inclusive. It means it does not, it goes right up to that point, but does not include that point. Okay. Other questions about that? Okay, so that's how we're going to do them graphically. So now let's go look at them with equations. Okay, so it's a, oh, wait. Okay. All right, before we go do equations, I was ready to go do equations, but we're not. First, we just want to get to sketch our own scenarios to kind of make sure that we understand this, okay? So here it says, sketch a graph with the following conditions. Sketch a graph with the following conditions. So we're going to come up with our own graph that would meet this condition. And I want to start by saying there's an infinite number of correct answers here. So there's various answers possible for all of these where we're sketching our own graph. So this is the limit as x approaches 1 of a function equals 3. The limit of the function function as x approaches 1 equals 3, okay? So can you come up with a graph that would be true for? What's important, what I know that I have to graph, is that as the function approaches 1, so I'm going to see where an x value of 1 would be, the y values have to be approaching 3. The y values have to be approaching 3. So I can make it continuous. I could plot a point there and just do a vertical line. Okay. I could make it discontinuous. I could do an open circle there, but just make it approaching that from either side before, even though it's not inclusive. Okay, so as I draw different possibilities, let me know if you don't see why that would work. Okay, so let me know what your questions are if you're not sure about that, okay? I could even do one of our natural log graphs, which we haven't seen for a while. So I could do a graph that had an asymptote there and hit that value and increase slowly and decrease super fast, okay? So there's an infinite number of graphs I could draw, but what's important is that the function be approaching a y value of 3 as x approaches 1. Okay, any questions on that? All right, so let's try the next one, and I want to see what some of your graphs look like. Okay, so the next one says the limit of g of x as x approaches 4, so that's as x approaches 4, equals -2. The limit of the g of x as x approaches 4 equals -2. Okay, so again, there's going to be various answers on all of these. Can you come up with one? That means as my x value approaches 4, 1, 2, 3, 4, my y value has to be approaching -2. My y value has to be approaching -2. Okay, so I could do an open circle there and have it be doing one of these if I wanted. Okay, there's an infinite number of things you can do.
Miss Weaver, does it matter if it's an open circle or a closed circle?
So it doesn't matter for this reason. So even if it's an open circle, as we approach from the right, it approaches -2. As we approach from the left, it approaches -2. So the limit is -2. Whether or not its actual value of the function at that point is -2 is not important, but as long as it is the same value as it approaches from left to right. Because if we just wanted to know what the function equaled at 4, what the function equaled at 4, we would just evaluate g of 4. Okay. Instead, we're asking what the limit is, what it's approaching. Okay. And that can be extra important when the function doesn't exist there, because we can still get information about where it's headed, even if it doesn't exist at the actual place that we're interested in. Okay. So let's try a couple more. So now we're going to take it up a notch. We're going to make our graphs a little more complicated. This is the limit of the function as x approaches -3. As x approaches -3 equals -1. And the limit of the function as x approaches +2 equals +1. Okay. So the limit okay, so what are we looking for there? Well, that just means as x approaches -3, we need the y value to be approaching -1. So I could make it an open circle, but I don't have to. Like, I can make this easy on myself. I can just actually plot a point there. Okay, and the limit of the function as x approaches 2, so that means at an x value of 2, it approaches a y value of 1, so I could plot a point there. And I could just connect them. I mean, like, that would be a function. That would still be true. So we don't have to make them crazy graphs, right? Like, they can still be simple graphs. That would still be true. But you have the freedom to do a variety of graphs. There's a variety of things it could be. Okay, like on this one, I could have actually, let me erase and do a different graph. Or we'll wait and do that. We'll wait and do that. Yeah. we've got more to show, so we can try other ones. -3, 1, 2, 3. And times the 2. So we could have a polynomial where it bounces, crosses, and shimmies. We could do all kinds of different things. Okay, let's still approach that. Okay, so let's see what you guys can come up with on this next one. It says as x approaches -2, the limit of f of x as x approaches -2 equals 4. And the limit of f of x as x approaches +3 is -3. So let's see what you guys get on that. See if you can come up with a graph on that. I need you guys submitting in the Pear Deck, right? So that I can see your graphs and see if the ones that you're coming up with are right or not. This is my chance to give you graded feedback before you have to do it on Delta Math, okay? So do share your screen so I can give you some feedback. Thank you, thank you. Right, so like if I was stressing about this, then I would just make them super simple. I would start with just having them actually be continuous and touch those points and just draw it connecting those points, right? But if I was feeling like, oh, I got this, oh, we can do this, we can do that, then I could try fancier things, right? So the limit of f of x as x approaches -2. So at -2, we need to be approaching +4. So a point there. As x approaches +3, 1, 2, 3, the function needs to be approaching -3. So it needs to include that point there. So you could either have a piece here, then I could draw in an asymptote if I wanted, so because it still needs to be a function, right? Like it can't fail the vertical line test, and then I could have a piece coming up through there. Okay, that would work. Or I could have just made it a line connecting those 2 points. Okay, there's an infinite number of things that'll work, but like I said, I did need to put an asymptote in there so that we knew that this side would approach that asymptote rather than crossing, because it's still got to pass the vertical line test. Okay, so I want to show some that are just a smidge harder. We won't do all 4 of these, but I want to do at least 2 of them. Okay, what's the limit of g of x? So I guess we're not asking, we're sketching. So this is still sketching. The limit as x approaches 4 of g of x equals 2, and the limit, and actual g of 4 equals 3. Okay, so what's that going to have to look like? This is why I wanted to do these. These are going to take it up a notch. So the limit as x approaches 4 equals 2. That means whether I'm coming from the left or the right, I'm approaching 2. That's the overall limit. But it tells us g of 4 is actually at 3. So what does that mean? That means we're going to have a closed circle at this point, because that's where the function actually is. The point is at 4, 3. So I'm going to come find 1, 2, 3, 4, and 1, 2, 3. Okay, so the function is actually at that point. That has to be true because that's g of 4 is 3. But the limit as g approaches 4 is 2, which means if I go to 2, I can switch colors. From the right and the left side, I have to be approaching that. So I can have a function that goes up there and goes down there, okay, or any other shape that I want in between. But from both the right and left, it has to be approaching 2, even though the function is actually up at 3. From the right and left, it has to be approaching 2 because that's the overall limit of the function is 2, even though the function itself is at 3. Okay. So there's another one there on your own that you can try there. We have answer keys in the left for that. Let's try this one at the bottom. That's a little bit different. This one says the limit as x approaches 1 from the right equals 2. The limit as x approaches 1 from the left equals -2. So as we approach from the right and from the left, it needs to look different. So you saw some examples of that earlier. Can you sketch one of your own? So at +1, as we approach from the right, it needs to be approaching +2. So I'm going to do this like that. You can do whatever you want. So far, as I approach from the right, it is headed to +2. That takes care of that. Okay. As we approach from the left, it needs to be going to -2. It needs to be going to -2. So, right. And you can do any kind of a shape that you want there. Any kind of a shape that you want there. Bonus question, can you tell me what's the limit as x approaches 1 of g of x? What's the limit as x approaches 1 of g of x? Does not exist because we're approaching different values. Okay, so now Noah, you asked why it was a closed circle. So on a lot of these, it didn't matter if it was open or closed circle. On the one right above, they told us g of 4 equals 3. That means the function evaluated at 4 is 3. So that has to include that point. So that's why we plotted that solid point there, because it told us that's where the function was at that point. Why is the circle on the left side closed? Remember, guys, we said there are various answers for all of these. So I just chose to make it closed. If you wanted to, Valerie, and that's why I said, show me your graphs, share your work in Paradox, so I can tell you whether or not what you're doing is okay too. I could have made it open as well. And that's why if you don't share your graphs, I can't tell if what you're doing is right or not. What I can tell you is that they can't both be closed. So why can they not both be closed? So Emily, what happens if they are both closed circles? Then it fails the vertical line test and it's not a function. So this is function notation g of x. All of our graphs have to pass the vertical line test, meaning that if I move it like a ruler or your hand is a vertical line across the graph, you can only touch one point at one time. So if one point is closed for that same x value, all other positions must be open, okay? And so you can have them both open, and then it would just be a discontinuous function, but you can't have more than one that's closed. So a couple of you, Taryn, you've got the double closed too. Okay, so just be careful. One can be closed, they can both be open, but they can't both be closed. Questions for me about that? Okay, so let's go move on then to equations. And you can always come back and look at these. Like I said, my answer key shows lots of different shapes of graphs that are possible. And it's in the folder as well, okay? But that's how we'll do it graphically. So let's do limits by substitution with equations. All right. So when we were drawing our graphs, the easiest graphs to draw were graphs where it was just a continuous function that included both points, right? And so we just like connect it, you know, it's just continuous and it automatically hits that value, that requirement that that's the limit, okay? So when we're looking at our limits here, if it's a continuous function where we're looking at it, all we have to go is see what the function value is there, and that's going to be the limit of it as well. So let's look at these first few. Let's read this notation. So this is the limit of 4 as x approaches 2. Now, when you see something like that that says the limit of 4, remember, this is our function. This is our function equals 4. That's all that's saying is our function equals 4. What does f of x equals 4 look like? Remember, f of x is just like y equals notation. That's just talking about the horizontal line where y equals 4. Okay, where y equals 4. It's just talking about that graph. Okay, so what is the limit as x approaches 2 of that function? Well, whether we're approaching from the right or approaching from the left, we're approaching 4. It's going to be 4 for that whole function. The limit of that, any x value on that function is going to be 4. because the y value is always 4 for that function. Let me know what questions you have as we go, okay? All right, let's try the next one. It says the limit as x approaches 5. The limit of x as x approaches 5. Well, there again, it'll be helpful if you'll realize that that's just saying our function equals x, or in other words, y equals x. Okay? So if you think about what y equals x looks like, that's the linear parent function. That's the linear parent function, y equals x. Okay. So, and you don't have to sketch it graphically. You can just think about it, right? Okay. But I was showing sometimes it's helpful to see it graphically, especially while we're newbies. All right. So it says, what's the limit of x as x approaches 5? Well, as you get closer and closer to an x value of 5, your y value is getting closer and closer to 5 as well. Y just equals x. The y value equals whatever your x value does. It just equals 5. Okay, so questions on those? All right, so let's take it up a notch. We're just going to let our equations get harder and harder.
Miss Weaver,
Uh-huh.
on the last one, how come the first one is 4?
So as x approaches 2, as x gets closer and closer to 2 from the right and left, my y value is 4. The whole equation is y equals 4, so y is never anything but 4.
Oh, okay.
Okay.
That makes sense. I get it.
No problem, no
Thank
problem.
you.
And I lost my little writing screen, so give me just a sec. Okay, so this next one, we want to look at the function and we want to think, is it a continuous function? If it is, we're just going to substitute that value for x in. That's why this is called limits by substitution. If it's continuous, we'll just plug it in and see which value it is at that point, and that'll be the value it's approaching from the left and right, okay? So is this function continuous? Just looking at it, is it continuous? It is. It's just a quadratic function, and so it's going to be continuous, okay? What's going to make our functions discontinuous is when we have a denominator of 0. So we'll talk about that in our next problem. But this one, I can plug in any number I want, and I'll get a continuous function here. So this is the limit as x approaches 3 of this function. So we're going to substitute in x equals 3. Okay? So 2 times 3 squared minus 3 times 3 plus 4. Okay, if I plug that in and evaluate it, 3 squared is 9, so 2 times 9 is 18. I'll just go ahead and do 2 steps in one there. So that's 18 minus 3 times 3 is 9 plus 4. 18 minus 9 is 9 plus 4 is 13. No, help, yeah, okay. I was like, oh, okay. So our answer is 13. Our answer is 13. Just evaluating the function at 13, at that value, we get 13. So if it's continuous, then we can just plug in the x value to see where the function will be. We don't have to graph it or think about it graphically. We can just see where it would be by plugging that value in. Questions for me about that? Okay, so let's, like I said, just continuing to take our functions up a notch, okay? This next one is a rational function. Way back first semester, I believe it was, we did rational functions. And so remember, this function will be discontinuous, okay? It'll be discontinuous. Okay, at x equals what? Well, remember, the restrictions that we have where we get a vertical asymptote or a break in our graph is where our denominator equals 0. So to find out where it's going to be discontinuous, let's go set that denominator equal to 0. Where does the denominator equal 0? It's going to be discontinuous where the denominator equals 0. Equals 0. It's going to be discontinuous where the denominator equals 0. So set the denominator equal to 0 and we'll solve for it. I'll add 3x to both sides, divide both sides by 3. And I get that it's discontinuous at x equals 5 over 3. Okay, it's discontinuous at x equals 5 over 3. Okay, where are we looking for the limit for on this one? We want the limit as x approaches -2. We want the limit as x approaches -2. It's okay that it's discontinuous at 5 over 3 because that's not where we're looking for the graph at. That means the graph is continuous everywhere else. So we're okay to still do substitution here. So if I've substituted in -2, I'm going to substitute in okay, so I'm going to substitute in, that's going to give me -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times -2. So I'm substituting it in, and then we just get to quickly do a little arithmetic in our head. Okay, so that's going to equal, I'll do it down here for a little more space. Okay, so -2 cubed is going to be -8. -2 squared is 4 times 2 is +8 minus 1 over 5 minus 3 times -2 is -6 minus the negative is +6. So 8 and -8 cancel each other out. That gives me -1 over 11. So since I substituted in, I know that is the limit because the function is continuous at that value we're looking at. The function is continuous at the value we're looking at. So we can just substitute that value in and see where the function's at, and that's what the function's limit will be. Questions about that? How did I know it was discontinuous? Because it was a rational function, and rational functions are going to be discontinuous wherever the denominator is 0. So that's one of the basic. Remember when we were looking for domain restrictions on functions, we looked for a couple of different things. We looked for where the fraction was 0, where the denominator was 0 in the fraction, and we looked for where the number under the radical on an even root was negative, because we can't take an even root of a negative. So those were our domain restrictions, and so that's what would make the function be discontinuous or have a restricted domain. Okay, so let's try some more examples. Okay, so the limit, and this time, this is asking the limit as x approaches 0 of 5x cubed, that is the cubed up there, 5x cubed plus 6x over x. Okay, so now we are in some trouble. This fraction will equal 0 when the denominator equals 0. This function is discontinuous at x equals 0. And 0 is the number we're looking at. 0 is the number that we're looking at. And so we have a dilemma. Remember, it's okay that this actual function is an asymptote or is undefined at our actual number, because we said we can have an open circle and still have a limit. We just need to know what it approaches as we approach from the right and the left. So therefore, we need an alternate form of this equation. An alternate form of the equation that we can evaluate to say, okay, so this function doesn't exist at 0, but does its limit exist? Where is the function headed towards? What would it be? What would it be? So we need to find an equivalent form of the equation. So let's see if we can do that by algebraically manipulating it to get an equivalent form. So this is going to be the limit as x approaches 0 of, and when I look at that, I see that both terms in the numerator have a common factor. So let's factor it out. If I factor out an x, that leaves me a 5x squared in the first term and a 6 in the second term. Everybody okay with that? I just factored an x out of both terms in the numerator. Okay, and I have the x in the denominator. Okay, that x in the denominator is the main reason that I wanted to factor that x out in the numerator, because now they'll cancel. And this just equals the limit as x approaches 0 of 5x squared plus 6. 5x squared plus 6 is not the same function as 5x cubed plus 6x. The only difference in their graphs, or rather, but they are going to approach the same value as you approach 0, but this function would be undefined at 0. This function would be undefined at 0, but this function would be defined at 0. Okay, so let's substitute in and see what it would be. Substitute. Okay, so we're going to substitute in x equals 0. So 5 times 0 squared plus 6. Anything times 0 goes to 0, so that just equals 6. And so the limit equals 6. Okay, the limit of the original equals the limit of this function, which equals the limit of this function. So this original limit is 6. The limit is 6. Questions for me about that? You have to know, okay. So what you have to be sure is that the value that you're evaluating it at does not make the function discontinuous there. Like say I didn't pay attention to that originally and just tried this problem. What would have happened if we just came in and started trying substitution? So it'll kind of take care of itself. Let me show you, Sarah. So if I hadn't thought about where it's continuous and where it's not, and if I just tried substituting in, I would have gotten 5 times 0 cubed plus 6 times 0 over 0. And as soon as I had that division by 0, that would have yielded that it was undefined. And so I would have known that I needed another form. Okay? So like on a couple slides ago, so this one, I didn't technically need to find out where it was discontinuous at because it wasn't discontinuous at -2. But you need to be able to realize that that's not going to do it. Or when you substitute it in, you're going to find out that it does it. Just like I was showing on this last one, because it'll give you a problem that's not defined. So if you want to try just straight substituting it in first, you can.
I guess I'm asking.
It looks like the boxed answer. Okay. So here it looks like -1 over 11. Here it looks like 13. Here it looks like 6. This is your work. You do have to show your work, but you asked what the answer looks like. The answer looks like 6. No. But when you're showing your work, that's why we're going to work in equations. This step equals this step, which equals this step. And you do have to use the whole limit notation, which will kind of drive you a little crazy at first. But that's where I'm like, suck it up and just write it out. Like the time you spend stressing over the fact that you have to write out the limit notation, it's actually good for you to practice reading it and saying it. It like helps you get familiar with it. And I know the instructions said that you would read this as the limit of 5x squared plus 6 as x approaches 0. That is correct. But you will often hear people read it as the limit as x approaches 0 of 5x squared plus 6, because often we're working on this part before we've rewritten this part. And so you will hear it read that way as well. Okay. All right. So let's try this other side of the equation. That means we got 10 minutes to go. So, or actually that one says flex time. I forget, it's my second block. I must not have an alarm set for flex time. Okay. So it is flex time. So if you feel like your algebra skills are up to handling the rest of the problems, then you can go ahead and go flexible. You can go ahead and go asynchronous and start working on your delta math. I do have some more examples of different kinds of equations in the completed notes. So if you got stuck on one, then you could just come back and look at the completed notes there if you want. Plus, I'm happy to work into flex time for anybody that wants to stay and look at a few more examples together. The limit equals 6, Valerie, because as you get closer and closer to an x value of 0, the function looks like 6. Like if we actually pull up a graph of that, so I think this is kind of interesting to note. We've got fancy calculators, so let's use them. So if I pull up the equation, it was 5x cubed. If I actually graph y equals 5x cubed plus 6x. And we put that all in parentheses. This one it'll be easier. X cubed plus 6 divided by x. Okay, so if I go and look at my actual, if I look at my actual graph of the function, Valerie, can you see that as x gets closer and closer to 0, the function approaches 6? Okay.
Yeah, I see.
Now, if we zoom in really close, I'm not sure how good the Desmos calculator does at showing open circles. Let's see if I click on that value, it'll show me. Okay, if I click on that value, do you see how it says 0 undefined?
Yeah.
So it doesn't show, just looking at it, it doesn't show that it's an open circle, but if I can go get right exactly on it, which is harder to do, I got lucky that first time that I clicked exactly on it. There it is. It shows that it is undefined there. So the function doesn't actually exist at 0, but its limit does exist. The limit of that function is 6 as x approaches 0.
Okay. Thank you.
Mhm.
So are you supposed to graph it to tell?
No,
what's-
no, but if you're having trouble understanding what's going on, then you can graph it to see what's going on. So we can do it from graphs or we can do it from equations. If
Oh,
it's a continuous equation, and this is a continuous equation, except for at that one point that it's discontinuous, then we know it's whatever the value would be there. And so we got an equivalent form of this. So if I graphed the equivalent form, if I graphed y equals, and what was our, let me look at what we ended up getting it down to. I think we got it to,
wasn't it 5x squared plus 6?
5x squared plus 6. Okay, so that's the equivalent form, only this one, because it's not divided by x, is not discontinuous there. That blue one actually is defined.
Oh,
Okay, so getting an equivalent form removes the discontinuity so we can see what the value would be, which lets us know what the limit actually is. Because whether or not it's an open circle there, it's still approaching that value.
yeah. Oh, okay. Thank you.
Okay, good luck. Mhm.
Thank you. Oh,
Right.
also, are you going to post a class recording anywhere?
I think I will this unit just because we don't have video notes. So
Okay.
just because we don't have video notes. So I think I will. Mhm.
Thank you.
Okay. All right. For those of you that have chosen to still hang around, I do want to show you one other kind of algebraic problem. So like this one, same thing. You're just going to factor this one. So this will just be, this is the limit as x approaches -4. Okay. And so this is going to equal the limit as x approaches -4 of x plus 4 over, we would just need to factor that denominator. We would just need to factor that denominator. Because if you plugged in -4, you would get a 0 there. So x squared factors to x and x. We can be pretty sure that one of the factors is x plus 4 because that's what our numerator is. So if one of them is +4 and we've got to make +12, the other would have to be +3. So that's where these kind of help you on your factoring, because you're pretty sure one of your factors are going to cancel. And now they do cancel, so that's just the limit as x approaches -4 of 1 over x plus 3. And now we can substitute into that form. Now we can substitute into that form. So if I substitute in, I get 1 over -4 plus 3, which equals 1 over -1, just equals -1. So the limit of this original function and this one equals -1. We're okay to put it down here or up there because we put equal signs between steps. This equals this, which equals this, but it's sometimes nice to go write it back by the original to remind you. This substituting in step is not equal to the others. This is a step we do to see what the value would equal. So we're solving the limits by substitution. Okay. Any questions on that? Okay, and then the last thing that we had that was a little bit different to look at, that's just more factoring. So those are all just factoring, which I think you guys can do. This one is reminding you that you can get rid of compound fractions by multiplying by the common denominator. So here my common denominator would be x. So I would multiply by x over x. So this would equal the limit as x approaches 1 of, when I distribute to that first term, the denominators cancel and I just get 1. When I distribute to the second term, I get negative x. Here, when I distribute to the first term, I get x squared. When I distribute to the second term, I get negative x. Now, this is still not ready to go. This is still not ready to go because if I plug in 1 here, I still get 1 minus 1 or 0 in the denominator. But now, oh, actually, I guess what I should have, okay. Well, there's more than one way. What I was going to say is that at this point, I was going to factor it back out. So I could have saved myself time if in the denominator, if I never multiplied it in. So I'm just going to go ahead and rewrite that, leave it separate. I'm going to leave the x out and the x minus 1. Okay, because when we're working these problems, we're looking for things that cancel. So that's why I would think, hey, maybe don't multiply that in. Maybe keep it separate. Okay, but I still can't cancel yet because in the numerator I have 1 minus x, in the denominator I have x minus 1. But what if I factor out a negative in the numerator? If I factor out a negative in the numerator, that becomes x minus 1 over x times x minus 1. And now I can cancel. So that gives me the limit as x approaches 1 of negative 1 over x. Okay, and now I can substitute. Now I can substitute in. So if I go negative 1 over 1, that just equals negative 1. So the limit equals negative 1. And that's a messy negative 1. So I can make that neater. Okay, questions on that? So the other one on the right just looks more complicated, but it's still the same thing where you would just multiply both the numerator and the denominator by the common denominator. So 5 times x plus 5 in both the numerator and the denominator. Let me recommend to you that you do just like what I did here, what I corrected myself to do here. Keep it separate as factors so that you can see if it'll cancel when you do that. Like here, when I distribute to the first term, the x plus 5 cancels. And so that gives me a 5 for the first term. When I distribute to the second term, the 5 cancels, and that gives me a minus x plus 5. And that's what I meant. If you'll keep it separate here rather than distributing that to 5x plus 25, then you'll be able to see what cancels sooner in the numerator or the denominator. On this lot in the denominator, there's only the 1 term, and so I'm going to leave that x out front with the 5 rather than distributing it so that I can see what cancels. Okay, let's go ahead and finish that one. That gives me 5 minus x plus 5 over, and I'm going to keep those separate. Okay, so the 5, oh, I didn't distribute. Okay, so when I distribute that, that becomes negative x and negative 5. Self-correction is a good thing. Okay. Now the 5 minus 5 cancels. That gives me, if you want to write it as another step, negative x over 5x times x plus 5. Then the x's cancel. So that just equals the limit as x approaches 0 of negative 1 over, and now I can distribute that to 5x plus 25. And now we can substitute in. So now if I substitute in 0, 0 times anything is 0 plus 25, that gives me negative 1 over 25. Negative 1 over 25. Okay. Since some of you are still with me, I'll show the last slide. Again, all it is a matter of the algebra for simplifying. So we just put tons of examples in there, more than we could get through in class, just so that you can look back and find examples of different kinds of algebraic manipulation. Okay. The last one is multiplying by the conjugate. The last screen is multiplying by the conjugate. So that's always good to practice, right? So that's going to be the last one that I show. Okay, so if I just substituted in 16 here, the square root of 16 is 4. 4 minus 4 is 0. I get division by 0 in the denominator, and so I know I need an alternate form. Okay, so I know I need an alternate form. So I start manipulating it. This is the limit as x approaches 16. Okay, so that's going to equal the limit as x approaches 16 of, so the question is, how do I want to manipulate this one? It doesn't factor as it is. We could see it as the factors of the difference of perfect squares in the numerator, but it would break down to x plus 4 and x minus 4, and that's not what we have in the denominator. In the denominator, we have the square root of x minus 4. So one thing we can do is we can always multiply by 1, but it's got to be the same thing in the numerator and the same thing in the denominator. So if we multiply by the conjugate, okay, then it can, we'll see what it does. The square root of x plus 4 over the square root of x plus 4. Whatever you do to the denominator, you have to do to the numerator, so that you're not changing the value of it, just changing its appearance. Okay, so the limit as x approaches 16. What happens when I multiply these two denominators? Well, what we love about multiplying by the conjugate is now we've created the factors that are the difference of perfect squares. So it squares the first term, so the square root of x squared is just x. And then minus 4 squared is 16. It's the difference of perfect squares. Now, in the numerator, I still have x minus 16 times the square root of x plus 4. And this is, again, where we're lucky because we don't want to distribute that because we're looking for things that cancel. And so by leaving them still not distributed, it's easier to see what cancels. The x minus 16 on top and bottom cancels, and this equals the limit as x approaches 16. And it's not even a fraction anymore. If the denominator is 1, we don't have to write it. It's just the square root of x plus 4. Now we can substitute into that because we won't get a denominator of 0. So now we've got it in a form that we can substitute in. Okay, so I get the square root of 16 plus 4. Square root of 16 is 4. 4 plus 4 is 8. So this limit equals 8. Okay, and again, that next one is just another example like that. The completed notes have all of those worked out in them so that you can go look at the algebra for any of those different styles of problems that you might see.